All right, so I'm not gonna go over where I do it step by step, but I did wanna give a little short video that kind of just goes over and explains everything a little bit more in depth. So here we go. All right, so the review starts and it talks about understanding conceptual questions about E. So you need to know E is Euler's number, that's that 2.71, and it's used to show continuously compounding interest. So that P equals E raised to the RT, it shows what happens if you have that continuous growth. So just kind of understanding that, know that natural log is the inverse of that, okay? Next thing was about exponent rules. You guys should have exponent rules down. You've done those since Algebra 1. So when you're multiplying, multiply the coefficients, you're adding bases. Depending on if it says no negative exponents, you move things down to the bottom. Power to a power, you're raising coefficients to that power, multiplying your exponents. So this is like 2 raised to the negative 4th, x raised to the negative 8th. So that's how we work through that one. And then finally, division of powers, you're dividing coefficients if you can. You can't in this case because it's 2 over 3, that's reduced. And then you're subtracting exponents. So only if they have the same base. So that's kind of looking at exponent rules. The next thing is talking about transformations. So determining how transformations affect your domain and range and stuff like that for exponentials. So remember your exponentials, you have like your exponential decay, looks like that, and then you have your growth that looks like that. So when you're doing exponentials, your domain is always going to be all real numbers, but your range is the thing that changes, and it's not your asymptote, wherever that is going to determine that. So if you look at this first one, this negative 2 moved your asymptote down 2, but there was no reflection, so you know it's still, this is a decay problem, so you know it's still up here. It just got moved down, so our range was negative 2 to infinity. But if you look at this next one, all right, domain negative infinity to positive infinity, it went up 6, so our new asymptote's at 6, so you know you have that in your range, but it also reflected, so it went from being like this to it got reflected, and now it's down like this, so it's going from negative infinity to 6. So I'm sure they'll ask a question about that. Make sure you guys kind of have that down. Okay, next thing, write exponentials given a graph. So when you're given a graph, it has to tell you what your base number is. So you can see that. So remember you have your parent function. You always have the point 0, 1, and then the point 1 comma your base, whatever your base is. So in this case, it's a 2. And then you're going to transform. So your points, your first points that you're given are 0, 4, and then 1, 3. So those are your transformed points. And then you kind of want to try to label any transformations you can. So your new asymptote is up here. So it went up 5. And if it's 2 to the x, 2 to the x usually looks like this because it's growth. Now it got flipped over, so you know you have a reflection. So if you look at your x values, it stayed 0, 0, 1, 1. X has stayed the same, so no transformations with that. But your y value, if you write a rule for reflection and up 5, that would be negative y plus 5. Plug in and see if it works. So if you plug in 1 here, negative 1 plus 5 is 4. That's good. Plug in 2 here. Negative 2 plus 5 is 3. That's good. Then you can write what your equation is. So reflection's the negative in front, and then plus 5 at the end moves us up 5. So that's how you do that one. Okay, next page. This is sketch the graph given your exponential function. So again, your parent function is always going to be 0, 1, and 1 comma whatever your base number is. And then you need to write your rules. So if we're going right 2, that means we're adding 2. If we have a vertical stretch by 3 and we're going up 2, that rule is 3y plus 2. So your x's are always opposite, your y's stay the same. So if you plug in for x's, 0 plus 2, that's 2. 1 plus 2, that's 3. Plug in your y's. 1 times 3 is 3, plus 2 is 5. 2 times 3 is 6, plus 2 is 8. Graph where your asymptote is, plot those points, and connect. Same thing happens over here on this side. You do the same thing over here. That one's just a decay, so it goes the opposite way. Write the domain and range. We just talked about domain and range. Domain is all real numbers, and then your range is always going to be from your asymptote to infinity or negative infinity to your asymptote. Next thing, determines whether something is increasing or decreasing, okay? So you need to think about what your parent function looks like first. So this parent function is 3 to the x power. 3 to the x, that's a growth that looks like this. But I'm telling you it got reflected, so it went from going like this to now it looks like this. That makes it a decreasing. From the left to the right, it's going down, 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 down. Okay? If you look at this next one, this is a decay, okay? Because it's smaller than 1. So decays look like this. But now I'm telling you that we're reflecting over the y-axis because it's negative x over here. So if you take it, flip it over, now it looks like this. That's an increasing function. So you need to make sure that you can work your way through it. Reflections are going to be the thing that changes shape, so that's what you're looking for. Then we get into logs. So change of base formula is this formula down here. I'm going to give you that on the day of the test. So basically it's just can you rewrite? So if I ask you to rewrite as base 10, log base 10 of the argument, log base 10 of the base, we know that base 10 is the same thing as log, so I just rewrote it over there. Okay. Evaluating, so if you're evaluating, you're going to set it equal to x and then you're going to solve. So this is 2, because that's the base of your log, becomes the base of your exponential, and then you flip-flop those two. So 2 raised to the x equals 1/16. You can rewrite 1/16 as 2 to the negative 4th, okay, because 2 times 2 times 2 times 2 gives you 16, but it's in the denominator, so it's negative. As soon as they have the same bases, 2 and 2, you can cross out and solve for x, so you end up getting that x is negative 4. If you do that on this next one, 3 raised to the x power is equal to 81. So you're thinking 3 raised to what power gives you 81? That would give you 4. So that's can you rewrite and solve. The next thing, which I would be shocked if they didn't ask a question about it on the test, is being able to simplify, so condense and expand. So when you're condensing, remember any coefficients you have are going to become exponents. So these become exponents. Anytime that you see subtraction, that becomes division. So condense, this would be log base 4 of a cubed over b cubed. Or you could also see it because they're both being cubed, you could do ab cubed. Either way would be the right answer. If you look at this next one, log base 3 of x, that's already simplified. This 2 moves up to become an exponent. Addition, you think multiplication. So this becomes log base 3 of xy squared. Expanding, you're going to try to break it apart into as many pieces as you can. So on this first one, we start with exponent rules. So we distribute that 3. So x becomes to the 9th power, 3 times 3, y to the 3rd power, and then you're going to break it apart into its 2 pieces. So you have log base 2 of x to the 9th, log base 2 of x cubed, because it's plus because this was multiplication, and then take your exponents and pull them to the front, and they become coefficients. That would be your final answer. This one works the same exact way, but this is subtraction because we're dividing here. Answer conceptual questions about the relationship of log properties and exponent rules. You should understand that exponent rules, when you're multiplying, you're thinking addition. So with log, when you're adding, you're thinking multiplication. So those addition, multiplication are always going to stay connected. Division, subtraction is always going to stay connected. Next thing, write an exponential in logarithmic form. I guess I should have done it the opposite way, but that's fine. So if you were given this and you wanted to work back here, the base of your exponential becomes the base of your log, and then these two things flip. So 1/8 and -3. You can, here, base of your log becomes the base of your exponential, and these two flip. So y to the x is equal to 76. Next thing is solving. So if you're solving, if you have two logs that are set equal to each other and they have the same base, so in this case they're both base 10, you can cancel the logs and then you just solve for what's left over. So 4p minus 2 equals -5p plus 5. And then you solve from there, p equals 7/9. If you have just one log, you need to isolate that log first. So on this one we divided by -6, We got log base 3 of x minus 3 is equal to 4. Then you're going to rewrite it as an exponential. So the base of your log becomes the base of your exponential, and these two things flip. So 3 to the 4th is equal to x minus 3. 3 to the 4th is 81. Add 3, x equals 84. Okay, so I'm sure there'll be one about solving too. Next, understanding inverse relationship of exponential and log. Just know, they're inverses of each other, and so that means everything is an inverse. The domain of a exponential is all real numbers. That means the range of a log is all real numbers. So everything is going to flip when they're inverses. Okay, next thing is sketch a graph given your log equation. So if you're given your log equation, you have to write your base equation first. So log base 6 of x, that's your parent function. 1 comma 0 is always going to be on your log, and then your base comma 1. All right, so this is like the opposite of exponential. And then you're going to write your rule. So if we're going right 1, we're going to add 1. Remember, those are always opposite. If you're going down 5, you're going to subtract 5. So that gives us our new asymptotes at 1. Plot those points, and then draw your log. Same thing happens over here on this one. This is log base 5. So how do those transformations change the domain and range? Because we're talking about logs now, your range is always going to be all real numbers. And then your domain is going to be from your asymptote to infinity or vice versa. So none of these got flipped. So it goes from your asymptote at 1 all the way to infinity. Your asymptote at -1 all the way to infinity. Next, write the log function of the given graph. Again, it has to tell you, so assume that it's log base 2 of x. So you do it the same exact way that you did it for exponential. So your starting value is 1, 0. That's your parent function. And your transformed point that you're given on this graph is 3, 0. You can start to look around and say, okay, well, I know logs are usually like this shape. So this one obviously got reflected over the x-axis. Our asymptote has obviously moved right too. So if you plug those into a rule, +2, well, 1 + 2 is 3. That checks. 0 and -0, those are the same thing. That checks. So you know these are your two transformations. Negative log base 2 of x minus 2. Always opposite of your rule when you put it in here. This one works that same exact way. Okay. Answer conceptual questions about logarithmic bases. Just understanding log bases are always become the base of that exponential. And then solve exponential functions. So if you're asked to solve an exponential function, you have to solve them where they have the same base. So 16 and 2, all right, those obviously are not the same base. So you can rewrite 16 as 2 to the 4th. And now they have the same base. So you'll have x, you can cancel those out. X plus 5 equals 4 times 3 is 12. Solve from there. If you come over here, yes, you can rewrite 16 with a base of 4, but you cannot rewrite 8 as a base of 4. So we rewrote both of them with bases of 2. 1/16 is 2 to the -4th. 1/8 is 2 to the -3rd. This gets distributed. So -4x minus 4 is equal to -6x plus 3. And then again, you're just solving. Again, I would be shocked if there wasn't a question like that. Estimating, you should feel good about estimating. So use kind of your perfect powers. So if you're thinking, if you have 5 to the x equals 150 and they want you to estimate, well, you know 5 to the 3rd power is 125. 5 to the 4th power is 625. So you know it's going to be, somewhere between 3 and 4. You should be able to estimate. Converting between standard and scientific notation. If you have a small number, you always get a negative exponent. If you have a big number, or if you have a positive number, you get a big number. All right, so that's just moving your decimal place around. Performing the operations in scientific notation. So if you're multiplying, you're going to multiply your coefficients. You're going to add your exponents. So if you multiply your coefficients here, you get 34.104. And then if you add 3 plus 4, you get 7. 34 is not a number that's between 1 and 10. So this is a big number that we're making smaller, which means it's adding to your exponent up here. So 3.4. Oh, this next one I didn't do. So the next one, if you want to do it with, that, sorry, I'm trying to think now. Then you need to make sure when you're adding and subtracting, they have to have the same exponent. So right now we have -2, we have -3. So you cannot add those two together and right off the bat, like you can't add 5 and 1.6 because they don't have that same exponent right now. So you need to choose to change one to meet the other, and you can choose either one is fine. So if you wanted to change this first one, right now it's 5 to the -2. If you want to make this even lower, like an even lower exponent, that means you need to make this number bigger. So these are always going to work opposite. So 5 times 10 to the -2 is the same thing as 50 times 10 to the -3. All right, plus 1.6 times 10 to the -3. Now that they have the same exponent, now you can add them together. 50 plus 1.6 is 51.6, and then you're going to keep your exponent. Now on this one, they do not, or this is in between 1 and 10, so we need to move this back. So again, if you make this number smaller, you need to make this number bigger. All right, so this ends up being 5.16 times 10 to the -2nd power. Honestly, if you get numbers that are like exponents that are that small, you can always just change them to standard and then go back to scientific at the end if you get confused. Why do we use scientific notation? Because it helps when you have things like very, very, very large numbers, like, you know, the speed of light or stuff like that, or very, very, very small numbers. So if you're measuring like the size of an atom, you don't want to have to write out point blah, 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 blah. So that's when we use them. All right, last page. This is all about the real world exponential stuff. So I'll have those formulas up on the board for you guys, like I said, but if Mario bought a rare coin for $5,000 and the coin appreciates in value each year by 9%, how would you write that? So 5,000, that's his starting. 9% is a decimal. And because it's appreciating, we're adding. If it was depreciating, you would subtract. So you end up getting this formula right here, and then you can plug in 10 years, you plug in 10 here. In 10 years, it's worth $11,836. This next one, suppose Heather has $2,000 to invest in her account. It's compounded continuously. So when you see compounded continuously, you know you're using this formula right here. She wants to leave the money in the account until it's grown to be $5,000. How long will she have to leave it? So 5,000 we want is our ending. 2,000 is our starting. E raised to the 10% as a decimal is 0.1, and we don't know our t. If you are solving for something that's in the exponent, you're going to have to use a log. So we divide it by 2,000. 2.5 equals e raised to the 0.1t. So then you can take natural log, and then of what it's equal to, 2.5 is equal to your exponent, 0.1t. Divide by 0.1, and you end up getting about 9.16 years. So if you want to have $5,000 in your account but not put any extra money in, she's going to need to wait 9.16 years. Okay, and then this last one, I really don't know if you're going to get one like this, but I put it on there just so you could have it. I know when you see continuously, you automatically think that it's that P to the ERT, but because it doesn't give you an interest rate, you can always write it this way also. So your final amount is that A of T, your starting amount is that A sub 0. If I'm doubling, that becomes your multiplier. That becomes what comes in here, but it's only doubling every 4 hours. So I need to do my time divided by 4. So if I plugged in 4 hours here, that would be the first time that it's doubled. If I plugged in 8 hours, that would be the second time, 12, third time. But you need to make sure you're dividing by that. If it was every 2 hours, divide by 2, every 5 hours, so on and so forth. All right? So that's your equation. And then it gives you a couple different ones where if the initial amount was 100, how many bacteria will there be in 15 hours? So that's plugging in 100 for your starting, 15 for your time. That's about 1,345. Then if your final is 350,000 and you're starting still that 100, how long would that take? So again, dividing by 100, and then you get 3,500 is equal to 2 raised to the t over 4. So rewrite as a log. That's going to be log base 2 of 3,500 is equal to t to the 4th, or t over 4. Multiply by 4, multiply by 4. That's how you solve for t. So 47 hours. All right. I get that's a lot of information. I hope that going over it a little bit kind of helped you understand. But if you have any questions, make sure you're coming in and asking before the test tomorrow. All right. See y'all. Good luck.